This is the Jet Propulsion Laboratory at Pasadena, California. Voyager 1 has made its pass at Saturn and has sent back information which is not only absolutely new, but completely unexpected. Saturn is a far more complicated world than we thought, and in some ways is distinctly unlike Jupiter. I've been at JPL for the whole of the encounter, and to watch the information coming in has been one of the most unforgettable experiences of my life. Over the past few days, our whole concept of Saturn as a world has changed, and we've learnt more in a week than we've been able to do throughout the whole of astronomical history. So let me begin at the very start of the main encounter. 2 days before closest approach, that was on November the 10th. Dr. Gary Hunt of University College London is a principal scientific investigator of the imaging team of the Voyager mission. So I began by talking to him about Voyager's path through space.
Yes, it's been a most remarkable mission because in this period of time we've now gone all this way to Jupiter with the dramatic discoveries of the satellites and the ring and of course the dynamic atmosphere, and made it after a period of 3 years out to the furthest extremities of Saturn.
As the Voyagers pass by Jupiter, they've sent back spectacular results of the planet and its satellites, and that means we're going to be able to compare Jupiter and Saturn, and they may not be so alike as people thought.
Yes, we've been trying to understand weather systems of other planets, and of course this is a unique opportunity looking at Saturn. And of course the satellites, what are they? They've been no more than point sources of light for a very long period of time.
Now, Voyager 1 is closing into Saturn, nearly 950 million miles away from the Earth. And even when still 50 million miles from Saturn, it began sending back spectacular pictures.
Yes, even at this distance, Patrick, we can see the rings with the main division showing up, and also, in fact, the evidence of Titan showing up in the picture as well.
Gary, what about these remarkable spokes? We can see them here, spokes, fingers, call them what you will, dark radial features, which really shouldn't be there. What are they?
Well, about not there, but certainly we've seen them rotating. I think the real paradox here is that we see them in the ring structure out as far as the B ring. We do not find them in the A ring. And I think that's an important part for the theorists to bear in mind when we try to explain them.
Is it dark material, in fact, do you think?
Well, certainly material could bunch up as they rotate around in the rings. That change of density may be important. So may also be the magnetic field around Saturn.
When Saturn's photographed, even through the world's largest telescopes, the Cassini division between rings A and B is totally blank, and yet it's anything but that.
Yes, I think this is the starting thing, is the presence of the 5 rings within the Cassini's division. The dark spots that you can see there, Patrick, are part of the calibration on the Vidicon faceplate. But in fact, the whole area around the Saturnian rings is far more complicated than we ever really thought before.
And there are new rings. Here's ring F, which appears to be clumpy and relatively thin. We also see satellite number 14, which appears as a small disk.
Yes, this outer ring was discovered by Pioneer, and the variation in density we certainly don't understand. But these outer satellites are very important in actually associating themselves with the structure of the rings and their positions relative to Saturn.
Interesting to note that these 2 satellites, both under 300 miles in diameter, may be the cause of the permanence of the F ring. They box it in, so to speak. This picture was taken 11 million miles from Saturn. Look at the inner of the 2 satellites, bottom of the picture. Well, that's orbiting between the A ring and the F ring, which you can't see properly on this picture, and the other's just outside the F ring. But let's come on to the actual disk now. To me, one of the most remarkable discoveries so far is that Saturn has a red spot.
Yes, this feature lives in the southern hemisphere. It's quite large, about 5,000 kilometers long. But in fact, it's not alone, Patrick. We are finding red spots in the other hemisphere too.
Do you think that this main red spot on Saturn is really similar to the great red spot on Jupiter?
I think there will be a lot of similarities. Indeed, many of the larger spots that we will find in both the atmospheres of Jupiter and Saturn will have the same meteorological characteristics.
And then in the other hemisphere, we have these remarkable brown ovals, which show up very plainly here.
And indeed, wave structures sitting in some of the lighter cloud bands as well. The cloud bands of Saturn are certainly less structured, but still very important and interesting.
So at the moment, all is going well, and there's tremendous excitement everywhere. The press room is crowded. There are monitors showing the pictures direct from Saturn. There are televised conferences and so on, pictures, press releases, and the constant clack of typewriters. Pressmen from all over the world are here, waiting for the latest news from Saturn. But we'd get nowhere without the spacecraft itself, almost certainly the most elaborate and most ambitious unmanned probe ever built.
I don't think so. I can just check out.
The project manager of the Voyager mission is Ray Heacock. I asked him whether the trajectory had been going according to plan.
Oh yes, the trajectory of the spacecraft is on a very good path relative to the encounter with Titan and with Saturn. The spacecraft trajectory is controlled by radio tracking the spacecraft, coming up with position information from the radio data, and from the use of photographs that we take of the satellites against the star background. We convert that data into position information. Then that's combined with the radio data. That position information allows us then to compute the maneuver that we put into the spacecraft in terms of the angles that we turn through using small hydrazine rocket engines, 2/10 pound thrust engines. All of those maneuvers have been very precise. The initial trajectory is very precise. So the some 230 pounds of fuel that we had at launch is more than adequate, and there will be ample fuel left over after Saturn to continue flying the spacecraft out of the solar system. Now, of course, communications with the Earth is carried out through the high-gain antenna, and at X-band, we only use 22 watts of power to provide the data back here to the Earth. The attitude of the spacecraft in terms of pointing the antenna at the Earth is achieved by use of a sun sensor up here and then a star tracker on the opposite side of the spacecraft. So the sun sensor provides us control in what we call pitch and yaw, and then the star tracker gives us the roll reference around the spacecraft. And locking onto those and then moving the biasing of where the sun is, we can track the Earth and maintain the communication. Now, power for the spacecraft is achieved with radioisotope thermoelectric generators. These are devices that take the heat from nuclear fuel decay and convert that heat into electricity with thermocouples. And right now, we're still drawing 430 watts of power to supply power for the whole spacecraft doing the Saturn encounter. Now, the science, of course, which is the thing that we're carrying out the mission for, we have a low-energy charged particle experiment, a cosmic ray package, plasma particles, very low-energy thermal energy, electrons and protons, and then, of course, the instruments that are on the scan platform, which can be articulated in order to point these instruments at a planet, at the satellites, or at the rings, in the case of Saturn. And, of course, the cameras are here, a wide angle and a narrow angle, 1,500 millimeter focal length camera. And we also have an infrared interferometer spectrometer, an ultraviolet spectrometer, and these provide composition information, and then a photopolarimeter. But on Voyager 1, this instrument's failed, so it's turned off and not giving us useful data. But on Voyager 2, that instrument's still functioning, and next year, of course, we would expect that we would get good data from that experiment.
That's on TTS.
But that's on the Ramtech.
I was asking about TTS. In other words, I want to be swapping processes about 10, and I want to know how long.
And this is mission control itself, the heart of the whole operation.
Was the pretext that we're, as an X-band, looking on 43 under changeover?
The control of the spacecraft is here at JPL. From here, commands are sent out to Voyager. They travel out nearly 950 million miles, taking 1.5 hours on the way. Voyager obeys. The information sent back is then collected at one of three stations, either Canberra in Australia, Madrid in Spain, or Goldstone in California, depending on which one has the spacecraft above its horizon at the time. One hazard is rain, because heavy rain does tend to blank out some of the signals. And there was a period when rain in Spain cut communications with the spacecraft for 5 hours. Luckily, it wasn't at a vital period, but we're all devoutly hoping that it won't happen again. These signals from Saturn are received at DSN, or Deep Space Network. This is the receiving station, not only for the Voyagers, but also for all the other planetary probes which are still operating. It's continuously manned and has been for years, so monitoring of the spacecraft never stops. I always think that the DSN is science fiction come true. When the signals have come in from the Deep Space Network, they're sent here to MTIS, Mission Test and Imaging Systems, and here they're made available for distribution. Steve Palante is head of MTIS. Steve, will you tell us just what happens?
The data comes down from the spacecraft out of Goldstone through the DSN network, And we pick it up over here in some of our hardware. We have synchronizers that strip out the telemetry or the imaging data from the telemetry, and then going through one of our computers, the one directly behind me, we go immediately to one of our disk packs. On this, we immediately store an image, and at the same time, we're building up in the Ramtech volatile display generator, which is directly behind you, an image that we will then send all around the lab on our closed-circuit TV system.
I always find it remarkable that so much information can be drawn from a raw picture which may appear almost entirely blank. Dr. Torrance Johnson is one of those extracting this information. I wonder if you'd tell us how you go about it.
On the right-hand side of every picture that we have coming down, we have a histogram, a graph of the number of picture elements within that picture which have any individual gray level from 0 to 255. We use that information then to decide how to re-expose the picture, if you will, in a digital way in the computer, setting the lowest gray level that we think will be interesting to 0, stretching the highest gray level to white. Thus, with a picture with low contrast, such as some of the pictures of the atmosphere of Saturn have shown us, is that we can take 10% variation between bright features and dark features in clouds of Saturn and stretch those in contrast so that that 10% variation goes to the entire variation between black and white.
In other words, once you have the raw data, you can call up whatever you want and enhance what you like.
That's right. A good example is the disk of Saturn, the rings of Saturn, and the F-ring and faint satellites are running around Saturn. So that trying to get all of those objects with very different brightnesses on a single picture is almost impossible, and yet we can take a single exposure which captures the information from all of those objects and then make 3 pictures which are exposed precisely to show the best contrast for each of those different areas.
This may be a difficult question to answer, but what is the most surprising thing you've found so far with regard to Saturn by this technique?
Well, I've got to say more or less the newest thing we've found, which was the discovery that the F-ring is not circular, it's eccentric. Not only is it eccentric, it looks like it's raving mad. It's got twists in it. There are several components of it. The F-ring does not follow nice Keplerian ellipses around Saturn. And that presents a major problem, I believe, for the dynamicists. We will be looking for gravitational focusing, disruption mechanisms. Right at the moment, that's very surprising. It's one of the oddest pictures I've ever seen in the space program.
The Voyager color pictures aren't conventional color photographs. The Vinicon cameras take 3 monochrome pictures with different filters, the first one in red. And next, the same view is taken in green, and that builds up, remembering that you have to compensate for the movement of the spacecraft itself during the exposure. And when the green is completed, the third monochrome is taken in blue this time, and when all those 3 are combined, the resulting picture is a color reproduction very close indeed to what Voyager actually sees. In charge of the imaging team of the Voyager mission is Dr. Brad Smith. What are the most interesting features you've found so far?
Well, clearly the most interesting to me are the ones that we understand the least, and those are the fine structure that we see in the rings of Saturn, this clumpiness in the so-called F-ring. But the thing that bothers me the most are these spoke-like projections, these finger-like projections that extend across the B-ring. We've been aware of these for about 3 weeks now, and I think it's safe to say that we're no further along in understanding them now than we were when they were first discovered. I've worked on a number of flight programs, Mariner missions, Viking, 2 Jupiter encounters with Voyager, and I can't think of any phenomenon that we've observed that has left us in the dark for so long as these spoke-like projections.
Could magnetic effects be involved in any way?
Well, I think that somehow or other they have to be, but in ways that we don't understand. There also seems to be some relationship between the conspicuousness of these features and the length of time that they've been out of the shadow, but that's only an association. It doesn't really tell us what the physical processes that are going on.
November the 11th, one day before closest approach, and the rings were becoming more and more interesting.
Really, to be absolutely honest, the rings have shown us things that we've never anticipated. The Cassini division is not clear, it's full of all these tiny ringlets, and of course we're seeing here material which really disobeys all the laws that we thought that would prevail. When we lined up the pictures, we thought it was our misidentification that was a reason the rings looked eccentric. Now, why they're eccentric, of course, is something we don't understand. Perhaps there are tiny satellites in there, or larger pieces of material that are shaping these particular rings.
Well, this is a composite picture, isn't it? Here, you put the two ANSI together, and that eccentric ring just doesn't agree.
That's right. So clearly we've got a lot to understand about the interactions of rings one with another, perhaps with satellites and larger material in their close proximity.
I must admit that I rather wish I'd been in your office this morning when you first got those pictures of the F ring, which appears to be knotty and also braided. When you first saw that picture, Gary, did you really believe it?
To be absolutely honest, we couldn't believe it. It was absolutely extraordinary. It reminds me of a piece of rope that has been twirled and is untwining, because you see considerable kinks in it.
This has certainly been your day, because Voyager 1 has made its closest pass of Titan, and you've got the best pictures you'll get for a long time, because Voyager 2 won't go so close. Well, what do you make of Titan?
I think Titan is incredible, not because the imaging has been able to solve any problems. Indeed, with the imaging system, all we've shown have been the polar hood and the extreme haze. In fact, I'd rather not describe it as a hood, but as a collar, because I have in fact seen brightening towards the polar region itself.
Well, you've had your one close look at Titan now, because Voyager 2 won't go anywhere near it, comparatively speaking, and therefore you had your one chance of seeing Titan from close range, and you had no glimpse at all of the surface. Does that worry you?
Personally, no, because in some respects, I think Titan is the outer solar system's equivalent of Venus. You remember that Venus is a massive atmosphere, and we found intriguing meteorology with the upper atmosphere going much faster than the surface. Perhaps that may be true of Titan as well. I don't think it's been a wasted mission in that respect. I believe Titan will, as our analysis proceeds, be the highlight, indeed the star of the Voyager 1 encounter.
We don't see the surface, but we're hoping to go back and have a future mission and use radar, as we do on Venus, to look at Titan.
Have you any idea about the surface yet?
No, but we think since it's large, it will be dynamically very active. We think it will be a fascinating object to study.
What about the temperature?
The temperature is the most interesting thing, because the temperature of the icy satellites of Saturn is lower than anything else that we've looked at up to now.
These smaller satellites are certainly very different from each other. What about Tethys with this long, icy, 500-mile groove?
It's a fascinating contrast because it's the first topographic feature we've seen on any of the satellites of Saturn. And it's particularly interesting because it's a long valley that's probably formed by faulting, so that says there's internal activity. Here are these dreadfully cold, icy worlds, and here's the sign of an enormous valley that's as big as the valleys we've seen on Mars and on Venus. And here it is on this tiny, cold, icy world.
There's no doubt at all that the surface is ice, presumably.
Well, we have the density measurements, and since the density is about 1.2, that makes it just a little heavier than water, so it's slightly dirty ice.
What about Mimas with its 80-mile crater, 1/3 the diameter of Mimas itself?
We were fascinated because as late as yesterday afternoon, we were arguing whether there were any craters on any of the satellites at all. Then the resolution was so low that we had a dreadful debate as to whether they were markings on the surface or topographic depressions. When this beautiful picture of this enormous crater on Mimas came out, then there was it came up on the screen and everybody said, there's a crater.
Complete with a central peak.
Yes, it's in addition, there are lots of little craters around it. So in addition to the fact that there's a big one that looks so familiar to us, it has a whole crater field around it.
If that were an impact crater, wouldn't Mimas have been broken up?
Well, I can only say that it didn't. We've seen on the little tiny satellites sizable craters, and we've even seen the ones on the little satellites of Mars and Amalthea, craters so big that they actually change the shape of the little planetary body, yet it's still there.
There's nothing comparable upon Rhea, which I know is a much larger satellite.
Yes, that's a fascinating one, because we see little craters, but then we see big, bright streaks. We don't know what those are yet, but just in a very short time, we'll get very high-resolution pictures, and we should be able to tell whether they're mountain ranges, valleys, great shear zones that break up the surface. There are maybe 6 or 8 or 10 different possibilities for what the bright streaks might be. In just a very short while, we'll know.
What about Dione? This seems to have a very varied surface with dark patches and intercrater planes and craters and white streaks that look as if they might be frost.
Well, there are two interesting things that show on it. First, there's a little tiny bright crater that sends rays almost all the way across the planet. So it looks like the familiar kind of thing we've seen on the other terrestrial-type planets. then there are the other bright streaks. And on these, there seems to be topography. There actually seems to be a double ridge on one of the bright streaks. So we think it's a mountain range, again, showing signs of internal activity on this little icy body.
Isn't it rather strange that you have internal activity on a world as small as Dione?
Well, in the planetary game, we've gotten used to the idea that maybe we look and see first. Because, of course, we were confident that nothing like the great volcanic eruptions on Io would take place. Yet they're there.
Wednesday, November the 12th, Saturn Day, and Voyager is due to make its closest approach to the planet, 77,000 miles above the cloud tops. 1 hour, 25 minutes later, as the signals reach Earth across a distance of nearly 950 million miles, we'll know what happened. On the television monitor, the countdown to close to encounter is approaching 0. Now we're getting the signals from Voyager as it rushes into its closest encounter with Saturn. Minus 0.00000020 at the moment, 19 seconds to go. And when that minus sign on the left hand of the fourth line changes to plus, then Voyager will have passed its closest approach from Saturn. Watch the figures, 12, 11, 10, 9, 8, and here we go. Voyager coming into its closest approach of Saturn, the closest a man has ever been. That's it. And hear the cheer from here in JPL. And Voyager has now passed its closest approach of Saturn. We've got the signals back, and it's now started its never-ending journey between the stars. It's drawing away from Saturn every second. Its speed has started to slacken, and closest approach is over. And this is what Voyager saw, as it passed by Saturn at a distance of only about 1 diameter of the planet away from the cloud tops.
One of the fascinating things, Patrick, has been the way in which the rings reflect sunlight onto the planet itself. We're seeing important shadowing effects, which may be important to the weather systems we see on Saturn. But of course, at the time of close approach, we were going under the South Pole. We'd be able to measure their characteristics for the first time. The belt zone structures, the light and dark banding, seem to go a long way down towards the polar region, and we can see small-scale eddies down there, rather like Pioneer saw when it flew over the North Pole of Jupiter.
We've had close-range views of Jupiter from both the Voyagers. Now we've had these fantastic close-range views of Saturn. But the two globes aren't exactly alike by any means.
At first sight, that may be true, Patrick, but Saturn is a very low-contrast object. In fact, some of the most distant views almost showed no detail. And one of the fascinating things that we've both seen in the last few days is that as we got closer, we can see through this veil of haze that covers the main cloud layers down to more familiar patterns that we can see of the main weather systems. One of the fascinating things, which I don't really understand yet, is that the belts and zones seem to have a very regular pattern, and we could identify the zones as white areas and the belts as dark areas on Jupiter. This doesn't seem to work for Saturn. There's far more spectral contrast, and we're not quite sure yet how to define a belt and zone.
Has this told you much about Saturn's internal heat source?
This is something which is in debate because the Pioneer measurements suggested that Saturn had an enormously strong internal heat source, and there is a suggestion that the results from Voyager that the internal heat source may not be quite as strong. So we're trying to understand the differences between the two sets of measurements, but certainly Saturn does have an internal heat source, and this is important in driving its weather system.
Is it the same as Jupiter's?
Yes, the mechanisms will be identical because both the planets are contracting. The question is whether the contraction and the energy released by that process is sufficient to equal the energy that we are now deriving. Now, if it doesn't, then of course, which is the initial interpretation of Saturn, then of course we've got to explain out this result by some other physical mechanism.
November the 13th, 1 day after closest approach. As usual, there was a press conference, and there were developments that none of us had expected.
I think there's no question that there's a direct identification of molecular nitrogen in Titan's, top of Titan's atmosphere.
Gary, this news from Titan is absolutely sensational.
I think there's certainly every suggestion this must be the greatest discovery of all our exploration of the solar system.
Indeed.
The chance, indeed, of a nitrogen atmosphere, something we've been searching for a long while, the possibility of a huge atmosphere, but of course we are dealing with an object which is out in the very cold reaches. So indeed we have all the elements for life form, hydrogen cyanide, propane, the acetylenes, hydrocarbons. It really is the most exciting thing that's ever happened. The idea of a sea of liquid nitrogen on the surface of Titan. It also means we have a wonderful focus for the future exploration of the solar system. Surely this must be the next place that we go to.
What do you think conditions are like on Titan?
Well, certainly the pressure is about probably twice the surface pressure of the Earth, but it may be very cold. It'll be well below freezing point on the Earth, almost down to liquid nitrogen temperatures. So it's extremely cold, so that the reactions taking place there have a very long time constant, take a long while to evolve. But surely the fact that these situations do occur on a body rather like the size of terrestrial planets must mean it's rather like having the Earth out there in cold storage.
This mission has provided one discovery after another. Dr. Ed Stone is Chief Project Scientist.
Well, I think Saturn has not disappointed us. I really expected, since we had such a rudimentary knowledge of the Saturn system, that we would be seeing many surprises. But as usual, our imaginations were not nearly up to what nature provided.
And what is most unexpected of all? Titan?
Oh, I don't know. In terms of unexpected, it's hard. I really expected the unexpected. I think if you ask what is some of the most interesting results, I think Titan is very interesting. The fact that we now see that it has a dense atmosphere rather than a thin one, that there can be some very interesting organic chemistry going on in the atmosphere. That's all very exciting and makes Titan a most exciting place to think of revisiting if at all possible. I think the Saturn's rings are equally exciting in the sense that we, for the first time, are seeing the true structure of the rings. It's, I think, one interesting commentary that what from Earth was called the Cassini division, it has in it more rings than we knew the whole system of rings had from Earth. I mean, it just shows you how a fundamental change it is in our view of the Saturnian rings. And in the satellites themselves, we moved from Jupiter, where the inner major satellites were rocks and the outer two were half water ice. We go further out in the solar system, we find there that the inner satellites are essentially all water ice, and we see our first satellite where methane ice has frozen out. Again, we see the progression of moving further and further from the sun to colder and colder regimes of space.
Voyager 1 has now passed its closest approach to Saturn and is moving outward, but Voyager 2 is coming in towards Saturn. In view of what's happened with Voyager 1, are you going to make any modifications to Voyager 2?
Yes, we will. In fact, we purposely delayed planning in detail the final sequence of observations for our closest approach for Voyager 2 because we knew that we were going to learn so much. So as a result, we will be replanning, and the whole near encounter will obviously be looking at the rings, making much more time-lapse photography of the rings because they're dynamic structures. We undoubtedly will be looking for the first time up close at both Enceladus and Tethys, the two which we did not image as well with Voyager 1, so it provides a complementary coverage. And we do have a different pass through this Saturnian system. We come much closer to the outer edge of the rings with Voyager 2. Again, a very exciting prospect.
So Voyager 1 has accomplished both its main tasks, Jupiter first and then Saturn. It's still sending back useful data, even though it's now speeding away from Saturn at over 30,000 miles an hour, and it will stay in touch for some years yet, even though it won't encounter any other planet. The fact that Voyager 1 has been so successful has got very important repercussions for its twin, Voyager 2, which is now on its way to a Saturn encounter next year. Had Voyager 1 failed to obtain close-range information from Titan as well as Saturn, then Voyager 2 would have had to have done so, and that would have been the end of its main career. But as things are, Voyager 2 can miss out on Titan and go on to a rendezvous with Uranus in 1986 and Neptune in 1989. But first, it has its Saturn pass, and it'll tell us even more than we know now. But Voyager 1 has shown the way, and it's been, I think, the most successful of all the unmanned space probes. It's already started its never-ending journey between the stars, unseen and eventually untrackable. But one thing is certain. Nobody who was here at JPL during the Saturn encounter, or who has watched a television screen, will ever forget Voyager 1.